the question is, if we want to maintain a kind of low output impedance or something like that, then what is wrong with using a transformer, some sort of transformer-like structure to gate that impedance transformation as opposed to what we did? And there's no problem fundamentally. Actually, that's done sometimes, particularly in discrete design, right? For audio amplifiers, they used to do that. And there are some trade-offs involved in doing something like that. Let's talk about it. So the idea here is that, for instance, if you have, let's say you have an output, you have an amplifier, right? Let's show it in an abstract sense. So it has a certain output resistance R out with some kind of V out, right? And then the question is, if you are trying to drive a load RL that's substantially smaller than that, then of course the problem is that if this load is comparable or smaller than that, you get a voltage divider here and you lose some of your voltage gain, right? So, and that was one of the reasons we wanted to make this impedance as small as possible. Now the question is, why can't we do this? Why can't we have a transformer like that and a transformer like that? And let's say make this a n-to-1 ratio, right? And what that does, it basically, if you look at the voltage, it lowers the voltage, right? But actually, if you look at the impedance seen looking into here, let's use a typical green for impedance levels. So this is going to be n squared RL, right? So if you have a large return ratio, you can actually get that, increase that, and then you don't lose as much voltage swing. So most of the voltage will drop across here, and hence will appear here. But when it appears here, it will be 1 over n. So if this voltage is V1, this AC voltage is V1 over n. Of course, because of that thing. But the current is n times larger. So if this current is I1, this current would be NI1. Right? And hence the total power that goes in for an ideal transformer is equal to the total power that comes out. You can't violate conservation of energy, obviously, but at least we hope. Believe it or not, was it this year or last year? Last year. One of the papers submitted to ISSCC, a very well-known university, from a very well-known group. Maybe you should have it. But had something that essentially said, well, we've come up with this structure using transformer that multiplies n, and what it boiled down to is that both voltage and current went up by a factor of n. And there was power gain somehow out of the passive structure. So, well, you can either win a Nobel Prize or not get your paper in. Well, the latter happened. But in any case, so no, I'm saying that mistake can happen. But now going back to this, so the question is, your question is, why do we do this instead? Now, this is a good question, and there are several limitations to something like this. So let's look at it first from a practical standpoint in a discrete design. In a discrete design, if you're it depends on what kind of frequency range you're trying to address, right? But DC cannot go through here, obviously, right? So if I wanted an amplifier that amplifies a voltage that includes DC, this may not be a very good solution. Because there's no way I can pass DC through the transformer. I mean, I can make it closer and closer to lower and lower frequencies, but I can't carry zero frequency, very small. I mean, there will be a lower cutoff frequency. And for audio application, that may be okay, because you know that we can't hear below 20 hertz. Many of us actually can't even hear 20 hertz if you try. Now, and the thing is that also there's an upper end to the frequency range, and that was actually done in a lot of low-cost audio amplifiers, and still is done in this kind of impedance transformation. Now, you have to remember also you're cutting down the voltage range, so your power transfer characteristic is not improved. In fact, it's degraded a little bit because there's no such thing as an ideal transformer, so your transformer will have some additional loss. But it makes your circuit design here easier in that one sense. So you could do it, but the other thing is that you have to remember these transformers are usually bulky. They're big, heavy, there's an iron core, right? And they are big things, they're not really tiny things. So that's one. Now, as for integrated circuits, that's kind of a different ballgame. Now, you can make transformer on ICs, on integrated circuits too. You do that all the time, but you can't see that the transformers that you have, the 0.6 or 0.7. You can get higher than that with some fancy stuff, but now the thing is that that will work for lower frequencies. We use transformers at very high frequencies, in fact, in our designs for various reasons. That's one of them, impedance transformation. But we're talking about tens of gigahertz. That's the range where those transformers become useful. At very low frequencies, they are not that useful. So your question is a valid one, and the short answer is that there's nothing wrong with it as long as it fits your application. Right? Any other questions? General about stuff? Okay, so in that case, let's go to our main discussion topic. And so today, let's try to do something new. What we'll try to do today, we'll try to build an op-amp. So let's come up with some initial specifications. So usually, most of the time when you start designing something, you usually have some idea about what it is that you're trying to design. At least before. Very few people say, well, let's design something. You usually have an idea about what it's supposed to do. So let's see what it is supposed to do. So let's say it's going to be an op-amp with a differential input. We want a differential input and a single-ended output. We're allowed to use two supplies, plus and minus. Let's say plus VCC and minus VCC. Let's first do it in bipolar. Right? And so let's say we have access to a bipolar technology, which gives you basically a standard bipolar technology, which gives you reasonably good NPNs and okay PMPs. The PMPs are not that good in terms of the gain bandwidth product is not as high as the NPNs, so we try to get stuff, the gains stages to be mostly NPN if you can. Excuse me. Now, also we want to design an op-amp in such a way that this VCC doesn't have to be an exactly fixed, predefined value. So I don't want to design an op-amp that only works for plus minus 12 volts. I want to make an op-amp that works over a range of voltages, let's say from plus 7 to plus 15 volts and minus, right? So that's the kind of op-amp I want to make. And then let's say how much gain I want. Well, let's say I'm kind of thinking about having a reasonably large gain that I can use in feedback loop to control everything and reduce the DC off error. So let's say a gain of, make it round, about 1 million or greater than the voltage gain of 1 million. And how about, and then I have to also tell you what the input and output impedances are. Well, what are the input and output impedances of an ideal op-amp? Well, the input impedance of an ideal op-amp is infinity, right? For voltage op-amp. But I know I can't get infinity, so I have to put a limit on it. So let's say I say an R in greater than 50 kiloohms and an R out. So let's say I want to drive a load that's, let's say I tell you an RL. An RL that's greater than or equal 50 ohms. So I want to be able to drive a load resistance RL that's greater than or equal 50 ohms, and this is 50 kiloohms DC. Okay, and I want to have a reasonable common mode rejection ratio and all of that we'll calculate. So we want to start with designing something like this. Now, there's another constraint that we talked about kind of implicitly, and we'll talk about much more extensively next quarter when we talk about the frequency response and the dynamics and stability of the op-amp. That's the constraint is that I want to get my gain, voltage gain, in as few stages as possible. I don't want to have 10 gain stages, basically. Right? As few as possible. If I can get it in 1, that's great. If I can't do that, I want to get it in 2, and preferably I don't want to go above 2. I mean, there are op-amps with these stages of gain, but we'll talk about that. And even larger. Those are kind of interesting pathological things.
Less than 50 ohms?
Oh, greater. Thank you. Greater than or equal. Thanks. Okay, so now I want to make an op-amp, and I have a bipolar technology. I have to tell you something about my transistors, right? So let's say my bipolars have a beta N of 100, a VAN, an early voltage of 100 volts. For the PMPs, let's say I have a beta P of 50, and a VAP, an early voltage for the PMPs that is about 50 volts. I have to start designing my amplifier, right? So let's go through that design process. Now, the design process, the design usually works like you start with the simplest thing that you think that will do the job. And if it does the job, you're okay. If it doesn't, then you look at it and see why it doesn't and what part of it is the limitation, and then you go and try to modify it. A lot of times that's the way we design it. So if I were to make it, well, I need a stage with differential input and single-ended output, right? And I need to see what kind of constraints I have on that in terms of that performance. So the simplest stage, I know a stage that has a differential input and single-ended output, right? It's a differentiative pair with that current mirror up there that kind of converts it to a single-ended output. So let's start with that. And my objective is by the end of this design, not to have any current source in my schematics, right? I want to have everything out of transistors. So I want everything to be kind of done with real devices. But in the process, I will of course use those because when I'm not trying to focus on biasing stuff, I don't want to worry about it too much. So for now, let's assume that I have some current source. And this is minus VCC. And then I know that if I take this differential pair and take its output and mirror one of the current sources, one of the output currents, and reflect it to the other side, I get something like that. Okay? Now, let's see what the gain of this thing is. Well, first of all, I have to see what bias current I have to use. Is there any limitation on what kind of bias currents I can use here? Any of those constraints those design specifications that I gave you would limit anything in terms of what's the minimum or maximum current I can use? Think about RA. What is the input resistance of this stage? Parametrically. What is the differential input resistance? 2R pi, right? Exactly. So this is 2R pi. If you get an R pi from this guy, R pi from that guy. So 2R pi has to be greater than or equal 50 kiloohms. But what is R pi? Beta over GM. The 2 beta over GM. These are GMN and beta A. Right? And 50 kiloohms. That tells me, and this is 200, so that tells me that GM should be smaller than or equal 200 over 50 kiloohms. Right? So 200 over 50 is multiplied by 5, it's 1,000 over 250 kiloohms. So this cancels the kilo is 1 over 250. It's 4 millisiemens. Right? So my GM has to be smaller than 4 millisiemens, so I can't have an arbitrarily large GM. So let's say I want to get my GM to be around 4 millisiemens. Let's say for the sake of argument, I'm okay. Actually, that's not a good way of designing this, obviously, right? So let's say I want my GM to be 2 millisiemens. 4 millisiemens is too marginal. It's right there. So if I make the GM of each one of these transistors 2 millisiemens, I should be fine. Right? So I know 1 milliamp gives me 40 millisiemens. Right? So 100 microamps gives me 4 millisiemens. So for each transistor, I should have 50 microamps. So the total tail current should be around 100 microamps. If I make this around 100 microamps, then it gives me 50 and 50, and I have, my input impedance will be approximately around 100 kilo ohms. So I meet my input spec, input impedance spec by a margin of 2x, at least in theory. So that gives me a limit, right, in terms of the current. Now, if that's the current, and also then I know my GM of each one of these transistors is 2 millisiemens. That's the GM. Now, the same for those guys. But now, what is the gain of this stage? Open loop, if it doesn't drop, open loop, and if it doesn't unload it, so it's not driving anything. What is the gain?
GM, R out, R1, parallel R1.
Exactly. GM times R out, which is basically RON in parallel with ROP. Now, what is RON? Oh, sorry, this is ROP. This is RON. So what is RON? right? So this gives me 2 megaohms. And how about ROP? It's 50 over that current, so that's going to be 1 megaohm. So it's a parallel combination of 1 megaohm and 2 megaohms, which is about 600 kiloohms. 660. Okay. So what is the gain of the stage as is? I mean, I haven't loaded it yet. What is the gain? It's 2 millisiemens times 600 kiloohms, so it's 2 times 600, it's about 1300, 1200, I guess that's 660. So that's 1300. So the voltage gain with no loading is about 1300. Okay? Now, that tells me that I need something else. First of all, it tells me that this is not enough to achieve my objective in terms of the gain specification because I'm far away from a million. Now, if I were to use another stage of the same kind of gain level, would I be able to get it in 2 stages? Probably, right? Because this is a little over 1,000. If I can get something a little bit over 1,000, maybe I can do it. So that's one way to go. The other way is to try to improve the gain of this guy. Yeah, we can go cascade. So my point is that you have different options, multiple branches. There are many different ways of doing this, and those are just 2 examples. Now, so let's try one, and then we'll come back and talk about the other approaches too. So now, if I were to say, well, okay, I really need another gain stage, okay, before I get to my output, and that has to have a gain of about 1,000. So what can I get to get a gain of 1,000? What kind of stage gives me gain? Reasonably high voltage gain. Common emitter, right? So I need a common emitter. But now let's say for a second, just let's forget about the biasing. So let's for a second say I could connect a common emitter here, like that. Okay. Now, would that work if I could connect them without worrying about bias levels? What kind of gain would I get? Well, first of all, for this to get a gain of about 1,000, this has to be a high impedance load, right? It has to be some sort of current source, active load, to get the high enough impedance. So this really will look like something like that, and some bias. Okay. Now, what is the input impedance of that stage? Well, let's talk about the gain. Let's say somehow we have to bias it properly. Somehow we have to maintain an appropriate bias. So let's say it's biased at 1 milliamp, right? So if it's biased at 1 milliamp, what is a GM? So let's say the current IC is 1 milliamp, just typical numbers, right? And what is its IC? So what's its GM? GM for 1 milliamp, what room temperature is about 40 millisiemens. And how about RON and ROP? At 1 milliamp, this is going to be 100K, because it's 100 volts divided by 1 milliamp, and this is going to be 50K. Right? So it's the parallel combination of those 2, and it shouldn't be too surprising to you that it will come out to be the same number, right? Because they have the opposite dependence on the IC. So basically, this product of GM, RO, and ROP is independent of IC. We did that before, right? Because if you think, just to refresh your memory, the gain is GM, RON in parallel with ROP. So in a bipolar transistor, this is IC over VT times VAN over IC times VAP over IC divided by VAN over IC plus VAP over IC. This is the common denominator, so let's cancel that with this, and this cancels that. So it becomes independent of IC. So effectively, that product is nothing but VA, and we've done this calculation before. So VAN times VAP divided by VT times VAN plus VAP. And as you can see, it's a unitless quantity. It's volt squared over volt squared. Right, so as a voltage gain should be. So what we see is that, I couldn't even tell without looking at the things, if that were my only circuit, if it weren't loaded or wasn't affected by anything else, that product would be something like that. And the parallel combination of these two, basically RON in parallel with ROP, is going to be about 33 kilo ohms. And here, RON in parallel with ROP is about 660 or 670, let's say, kilo ohms. Okay? So, I don't need to worry about this now. I know what the product is. So, the gain AB2, let's say, is going to be 1300. Presumably, right? If everything were perfect. And would that achieve my gain objective? Yeah, it seems that 1300 times 1300 is okay. But now, let's see what happens in the first stage. If I just could, and again, assuming that the biasing is not affected or nothing is bad happening. If I just hook it up directly to here, would the gain of the first stage remain as high? Of course, it will drop because there's an additional impedance, right? So the new output impedance, so the gain of this first stage, which used to be GM and times RON in parallel with ROP, is now going to be RON in parallel with ROP in parallel with, let's call this R1. Because you have to calculate the total impedance on that node to ground, which includes now what you're driving. So if I just hook it up like that, what is R1? What is the input impedance?
R pi.
R pi. Now what is that, the value of R pi? For 1 milliamp.
Over I.
It's beta over GM, right? Or beta RM. What is RM? So this is 25 ohms. So beta times that is 2.5. 2.5. Right? 2.5K. This is another useful number to remember. For 1 milliamp, you have 25 ohms. RM is 25 ohms. Which is 1 over GM, basically, 1 over 40 milliamp. And then you multiply by 100 R pi. So it's 2.5 kilo ohm. You can see the problem right there, right? This guy is in parallel with that. Now that's going to cause you a lot of problems. So your new gain, so this is 670 kilo ohm. Well, your new output impedance is practically 2.5 kilo ohms. Right? Those guys don't matter anymore the way it is. And even if I could hook it up directly here, which I can't, we'll see in a second, this would give me what kind of gain? So it's 2.5 kilo ohms times 2 millisieverts. What is that gain? 5, right? Milli cancels kilo. So you drop your gain from 1000 to about 5. So it's obvious we need something in between. Right? And you can guess what we need. I mean, that's obvious at this point, right? You need a buffer. You need a buffer that has a higher input impedance and kind of increases the input impedance and lowers the output impedance so you can drive something. But even if I could do that, so let's say if I didn't have the gain problem, could I directly hook this thing up here? Just kind of connect it. What happens? Now, well, this maybe should be, let's say, minus VCC. Look at this and tell me what happens if I do this. From a DC perspective, from a biasing perspective.
Is there any feedback associated with this?
Well, not at the moment.
But there could be.
Well, yeah, but that's what, yeah, there could be. But what I'm getting at is even independent of that. So think about it. When the state is trying to kind of if you're trying to maintain, so let's go back to your kind of feedback approach, or it doesn't even have to be that way. So ideally, what the DC levels are. Look at the DC levels. What was the DC level of this stage without that? This point. VBE below VCC, right? So VBE below positive supply. Right? Now, what is the DC level? So, from the left-hand side perspective. From the right-hand side perspective, what is the DC level here? VBE above minus VCC. So, if this, let's say VCC is 10 volts, this is probably 9.3 volts. I mean, this wants to be at 9.3 volts when it's happy. This wants to be at minus 9.3 volts. And they're far apart. So you see the problem right there. So how do I fix that? I mean, I'm talking about something like 18.6 volts difference that I have to maintain.
Put a resistor.
Put a resistor there. Okay, so let's talk about that. Let's see what happens. Let's say you say put a resistor here, and you want basically. I assume that you're thinking about putting a resistor there to make a voltage drop. Okay, so let's talk about that first. So if I had a resistor like that, so the voltage drop across that resistor is determined by what? Which is the base current, right? So it's a small current, so this resistor will have to be very large, but that's okay. Let's say you can even live with that. So if I could make this resistor very large, so So let's say the base current for this, what is the base current? If the collector current is 1 milliamp, divided by 100, divided by beta, which is 10 microamps, right? 10 microamps. And I want to drop how much? 18.6 volts on 10 microamps. So 18.6 divided by 10, which is 1.86 divided by 1 micro, which is 1.86 megaohm. Okay? Well, it's a lot worse than that. This, so what happens is that, well, yeah, let's say we can make it 1.86 megaohm. Let's see what happens. First of all, tell me what is the gain from here to there? The voltage gain. How do you determine it? Well, you know this impedance, and you know this impedance, so it's a voltage divider, right? This is a resistive divider. What is the divider ratio? It's 2.5 kilo ohm divided by 1.86 mega ohm plus 2.86. 2.5 kilo ohm, which is practically 2.5 kilo ohm divided by 1.8 mega ohm. So right there, you lose about a factor of 800 gain. So it has a gain of 1 over 800 approximately. Okay, so let's say even I could live with that. I can't, but let's say I could, right? Would this work? Or let me just propose something even better. Let's say I could put my hand in my pocket and bring this magic black box that effectively behaves like this. And say, well, you actually are allowed to use this. You want it to drop 18.6 volts? I give you a battery. 18.6. So you don't have that problem with the drop, right? With the gain loss. Because it's from an AC perspective, it's short. Right? If you could even use a battery, would this work?
Or capacitor. Or capacitor.
Well, or capacitor, but the capacitor has always a low cutoff frequency, right? It can't pass DC. So then you have to think about that. The battery, the good thing about battery is that battery is a capacitor which works down to DC. And has a fixed initial condition. It's an infinite capacitor that works. It's an infinite capacitor, basically. An ideal battery. Okay, so would this work? What would this violate? From a gain perspective, it actually does work now. Right, so you can get the gain. But one of the other things that I wanted to achieve in this design will not be achieved if I do this. I said I don't want my supply to be limited to one value, right? This was the value for 10 volts. What if I make my supply 11 volts, plus minus 11 volts? Then this value, because this guy is a VDE below this 11 volts, so now this becomes 10.3. This is a VDE above minus VCC. This becomes now minus 10.3. So this voltage now has to be 20.6 volts. So even this doesn't, this only works for the exact value of VCC. It's a bad way of designing things. You can never maintain VCC constant. Even if you're using a battery, the battery in the beginning of its life and the end of its life will have a different voltage, demonstrate a different voltage. And even if that were not the problem, the case, you may have other things that draw current out of a real battery, and because of its internal resistance, that voltage, the voltage that the battery presents to you is going to be different at different times, right? So even that's not going to happen. I mean, that's not realistic to assume that your supply voltage will be one single value. Yeah, you can think of, there are certain situations where you have a complete regulator outside that maintains that voltage for you. And in those cases, you can assume that, but even the regulator does not guarantee exactly constant value. There's some fluctuation. Any regulator has a specification of what's the maximum plus minus 5%, something like that. They tell you. So you see the problem, right? The problem is that the problem is somewhat fundamental because this guy references this voltage to ground, I'm sorry, not to ground, to minus VCC, and this guy is referenced to plus VCC. So the only way I can deal with this problem is what? If both sides were referencing that level to the same supply, either minus VCC or plus VCC, I don't care. One of the two. So let me show you one simple way of doing that. Well, what if I make this a PMP common emitter stage? So, well, the way to make it a PMP common emitter stage in my schematics is very simple. Apply input here and make this empty bias. So this becomes your current source. This is the complementary structure, right? And that becomes your gain stage. Now, how about this? Does this work from DC levels? perspective? Yeah, it kind of does, right? Because you look at it and say, well, this is a VBE below VCC, and this is a VBE below VCC, plus VCC. So now if I make my VCC 10 volts, it still is a VBE below that. Both of them are VBE. So they're both referenced. They're floating with respect to, they're referenced to that, so they move up and down. So this is that level. This is the VCC. This is this lower level, right? That low. So they move together. So even if plus VCC and minus VCC are not equal in absolute value, that works even, right? So in op-amp design, I have to be very mindful of that. And you will see this in op-amp design. That determines what kind of stages you can use and which one will be NPN and which one will be PMPs and things of that sort. And this is not the only way of doing it. But you may say, well, why do they do both stages in NPNs? I mean, you can do both stages in NPN. You can do everything in NPN, actually. But you have to think about it in a different way. You have to use slightly different kinds of stages. And we'll see a couple of examples of that later. So, but this, at least in principle, works for me, right? At least in terms of DC levels. But I know that this doesn't give me the gain, right? Why doesn't it give me the gain? Because this impedance is still, well, this time R pi, it's R pi P, because now I have to use the beta of P, which is 50, which is half of that. So my input resistance is, let's call this R1. That's about 1.25 kilo ohms. So it's even worse. So now my gain instead of being 5 is 2.5, if I do it this way. The first stage is gain. And I haven't even put my load resistor there yet. Because once I put, so think about that. If I put my load resistor there, just directly as is. Right? So let's say it's a 50 ohm. So what's the gain of the second stage then? Well, the output impedance is 50 kilo ohm in parallel with 100 kilo ohms in parallel with 50 ohms, which is 50 ohms. 50 ohms times 40 millisiemens. That gives me a gain of 2. And combined with a gain of 2.5, my op-amp has a gain of 5. Very impressive. Right? So now, obviously I have a problem, but this is not a very bad problem, right? In the sense that I know I have a stage that gives me this impedance transformation, right? Which is a common collector stage, which multiplies whatever impedance you put in its emitter by 1 plus beta. So every time you introduce one of those, you increase the impedance by factor of practically beta. So if I think about it, before I even jump in, I say, well, if I put one buffer stage here, what is the impedance I will see now with that in here? It's beta times that, right? Beta is about 100. So I go from 1.25 kilo ohms to 120 kilo ohms, which is still much lower than 1 mega ohm and 2 mega ohm, but it's better. So probably I need another one if I don't want, I need probably 2, right? I want to get this multiplied by beta squared, right? So if I get beta squared, that gets me to about 10 mega ohms, or 12 mega ohms, which is good because then it wouldn't load this guy too much. Fair enough? Okay, so now there's another reason to use 2. Let me show it to you. Let's say for the sake of argument, you were happy with 1 somehow, right? So your levels were such that, or the gate levels that you were expecting were such that you were happy to use 1 buffer stage. So you want to use a buffer stage. You want to use a buffer stage between this node and that node. Okay. What would you use? What kind of stage would you use? What's a buffer stage? A follower, right? A common collector. What kind would you use? The NPN type or PMP? PMP type. So, or MPN. MPN, yeah. So, this goes to VCC, right? Let's use a kind of ideal current source for now. Right? So let's say I have an ideal current source. Here, I bias it at some level. And then this goes here. Okay? Now, look at the DC levels. Am I still okay? Think about it. This node was, let's say, I showed kind of symbolically, say, minus VB. Well, let's kind of show it this way. Say, minus 1 means that it's 1 VB below. going to be 1 VBE. So I have a conflict, right? So what happens is that this tries to pull this down, and this tries to push it up. So what happens is that this, when it's pushed up, this guy has to push up, so this pushes it up here, this gets saturated, and this gets overdriven, and this guy gets saturated. So both this transistor will go into saturation if you actually connect it like that. You have no gain, because in saturation you don't have to go up a high output beat and GM. It doesn't do what you want. So now it's clear that I have to somehow drop another VBE from here to there. Go up a VBE. Well, I went down 2 VBEs. I need to go up 1 VBE to be at the right level. How do I go up a VBE?
PMP or
Yeah, I use a follower, but I use a PMP kind. Right? So, well, let me just erase this. Already gone. So this is my original follower. So this is the output, right? So I want to go up. So I use a PMP. This is minus VCC. It's going to make a ray here. And then I need a current source. Bias this. So this is the follower. So now, this is the second follower. So this is minus 2. This goes up. So this is minus 1. And now, if I use this to drive my common emitter, look like that. Well, all right, let's keep it like that. This is again another way of saying it's a current source. Then I'm okay because now it's a minus VBE and this should be minus VBE. So when I go up here, it will be a 0. And this will be a 0. Right? I could do that, right? This is doable. So you see that I use an NPN and a PMP follower to get to the stage. Now, these are not a problem as far as that constraint. I say, well, I want to get my gain in as few stages as possible, because these are not gain stages, right? We briefly talked about this gain bandwidth product. We said you only limit your bandwidth when you have high gain, but these guys have a sub-unity gain. So they're not going to be affected too much. But now let's calculate the gain, the AC gain, for this stage, right? For what we have right now. So now the other thing I need to do, really, well, not worry about that for a second. Sorry. Okay, so to calculate my gain of the first stage, what do I need to know? I need to know the impedance on this node. Well, from this node to ground, really, to AC ground. I know 2 parts of it. It has 3 parts. I know this part and that part. But there's another part, which is this part, the input impedance looking here, that I don't know yet. Well, how do I calculate that? Well, I know this. I know this is what? This is R pi P, which was 1.24. Let's say just R pi. This is 1.25 kilowatts, right? We did calculate that. It's beta P times, or divided by its GM. For 1 milliamp of current, so let's say this branch is a current of 1 milliamp, bias current, that's 1.25 kilowatts. Now, what is this impedance? Looking to the base here. Yeah, beta plus 1 times that. So for all practical purposes, beta times that, right? But it's the beta of the PNP. This is the PNP. So it's about 50 times that. So 50 times that gives you what? 75. Actually, you're right. No, it's 60. Yeah, 60. 62.5. So let's say 63 times. Okay, so that's 63 kilowatts. And then I have to go up another beta, but this time it's a beta of n. It's beta plus 1, not like 4, right? It's beta, right? It's about 100 times that, so that's basically 6.3 megaohms. So I'm okay right now, right? So because right now I can see I have 1 megaohm compared to 2 megaohm compared to 6.3 megaohm. So I'm not limited by the load anymore, right? So I have to calculate that parallel combination, so whatever that is. So it's probably going to be around 600 kiloohms, right? It used to be 670, but now because of the 6 meg, I would say it's approximately 600 kiloohms. You can do it exactly if you want. It's going to be in that ballpark. So the total impedance on this node is 600 kilo ohm, and multiplied by GM of 2 millisiemens. So that gives me a gain of approximately, so 81 is now approximately 1200, which is good. I didn't lose a whole lot. This is an approximate calculation. Okay, so I'm okay for the first stage. Now, how about the second stage? Do I have enough gain now? Well, I have enough gain without a load. If I don't put the load there, I know what my gain is. It's a gain like 1300 or something like that. Right? But now I need to drive a load. So how do I drive a load? Well, obviously I can't put my 50 ohm here, and I have to do something about that. So I have to think of a way of making this stage to be able to drive a load. So but obviously I need another buffer stage. Right? So would one buffer stage be enough? Let's say, how high would it get my impedance? One buffer stage, one collector, common collector, or emitter follower stage. Same thing. It brings up the impedance by a factor of what? Beta, right? Right. That's what we did here, right? Beta, beta, beta. So it went up to beta. So it gets 50 ohm to a beta, multiplied by beta, let's say 100. So it gets me to 5 kilo ohms, which is still quite low because I remember these two impedances were what? This impedance was, I think, so let's calculate 1 milliamp 50 ohms, that's 50 kilo ohms. This impedance was 100 kilo ohms. So it gets me to 5 kilo ohms, which is still substantially smaller than what I need. Right? That's not enough. So I need at least 2, probably. Now, but this time, I remember one thing, that in principle, this node, how high can it go or how low can it go, this node, in terms of the voltage swing? Large signal. So, what is the highest voltage this guy can take?
VCC minus VBE.
VBE. Why VBE? VC sat, right? The saturation voltage. So, it can be about 0.2 volts below VCC. And on this side, the same thing, because this guy is basically a collector. It can go as low as 0.2 above minus VCC. So, this guy has reasonably large swing, right? So, I can maintain that. If I can maintain that, that would be nice. But let's worry about getting the gain there first, and then we'll worry about this kind of what's the voltage swing at the output. So I need 2 buffer stages, right? So I can basically use 2 common collectors. Like that. That's the first step, right? I say I know a buffer stage that gives me high impedance. So if I use something like that and then use that to drive my RL, this is the output of the op-amp, of 50 ohm. So what that does is that, let's say, this will get multiplied by beta approximately. Well, it's a little bit more than that, right? I mean, if you want to do it exactly, beta plus, this is 50 ohms plus Rm of this guy, right? In general, it's this resistance plus whatever you see in the emitter. Gets multiplied by 1 plus beta. Now, in general, if the impedance is on the kilo ohm range, that Rm usually doesn't matter. It's on the order of several tens of ohms for 1 milliamp, right? But now, if it is running at, let's say, a milliamp again, now this is 25 ohms, this is 50 ohms, so I have to take that into account. I can't just drop it. So 75 ohms multiplied by beta 100, so that's 7.5 kilo ohms approximately, right? And now that goes up there to what value? Multiplied by another beta, so that gives me 750. This time I don't have to worry about this Rn, right? Because it's 7.5 kilo ohms plus 25 ohms. Kilo ohms approximately. So that's okay, right? 750 is reasonably higher than these 2, so that gives me that probably makes that 33 kilo ohm, 30 kilo ohms. Right? Approximately. So 30 kilo ohms times the GM of this guy, which was 40 millisiemens. 40 times 30 is 1200 approximately. So 82 is approximately 1200. So it's 1200 times 1200, so okay, so 1.4 mega gain, right? Okay, so at least in theory, it seems that, at least in principle, at least from a small signal perspective, I have the gain. Now, and this is an op-amp for you. Technically speaking, this is an op-amp. And even before even that Now, okay, but let's see what are the limitations of this op-amp. Can you see any limitations if I just use it the way it is? First of all, well, I have to turn these current sources into a realistic thing. I have to be able to generate this voltage and all those things, and I'll do that as the next step. But before I do that, let me ask you this question. Do you see any other problem with this op-amp? What are the potential problems with this op-amp? The way we design it?
Will the supply voltage like be higher for something like this? Like if you were to somehow like reduce the number of stages that we have like two followers, we have this, like would this like require a large supply voltage, or would the supply voltage be like 10 or 15 be something like?
Well, depends on what you're trying to achieve, right? I didn't give you any spec on the output voltage swing, right? But ideally, you want that output voltage swing to be as large as possible, right? So let me ask you this question now. What is the output voltage swing?
Isn't the minimum output voltage limited by the current source driving?
So that's one thing. So you said, well, I just kind of implicitly say this is 1 milliamp, right? Because I said this is 25 ohms Rm. So if this were running at 1 milliamp, so how low can this voltage go? What is the lowest? Well, the lowest is when this guy is completely off, right? It can't source any current. So even if this guy were not there, what is the lowest voltage this output V out can be?
-0.05.
So
Minus
-0.05 volts. So it can't go too low. It pretty much doesn't have any negative swing. We talked about this when we were talking about output stages last time. Now, how about the positive side? Does it go all the way to VCC or close to VCC? What is the highest? The out max.
That's some saturation, so like VCC minus VC sat.
Well, this node can go to VCC minus VC sat, right? Because this guy gets saturated. But when this is at VCC minus VC sat, what voltage is this node at?
VB lower than VB lower.
VB lower. So it's 2 VBEs plus a VC sat. There's a VBE here, there's a VBE here, there's a VC sat here, right? So if I want to use my kind of really rough notation, I would say the highest this can be, so this has a range, the highest this can be is, I would say, minus 0.5. But 0.5 would be VC sat. It's not exactly half of that, right? Or let's even just say minus 1/2. Or whatever. It's not really 1/2, right? I mean, in terms of VB, it's not even a VB. And this guy's going to be minus 1.1/2. It's going to be minus 2.1/2. So it's going to be 2 VBEs plus VC sat below VCC. So if your VCC is 10 volts, this can only go up to 8.4 volts. So it's not as bad as the other end, but it's not good either, right? If your VCC were 5 volts now, then you are losing about 30% of it. If your VCC were 3 volts, then you're losing about half of it on that side. So it depends on what your VCC is. So in that sense, it's basically plus VCC minus VCE sat minus 2 VBE on. Okay? So, well, I have two problems, but one of them is really a lot more serious than the other one. Which one is more serious? The negative one, right? This is, I basically get no swing on the negative side. So if I put a sine wave in, what I get at the output is, if it's large, ideally I want to get this. But now I get this. If I want to have a full swing, plus VCC minus VCC. We make it just a large right value of the input. So first I have to deal with this problem. So let's deal with that first. And then I have to think about what I do about this, if I want to deal with that or not. So how do I deal with that? How do I solve this problem? One way is to increase this current incredibly, make it incredibly larger, right? If I make it 1 amp, this can go to minus 50 volts, which is too much. If I make it 100 milliamps, then basically 100 milliamps times that gives me something like minus 5 volts. But that's a lot of current. But we know how to deal with this problem. There's a better way to deal with that, right? Using class AB, kind of a variation of push-pull at the output. So let's do that. What happens is that it does work, but it creates a dead zone. So if I put that in, it gives me that. We saw this last time. Because it takes a plus VBE, at least for this guy to turn on, above 0, and minus VBE above 0 for that one. So I need to maintain a certain minimum level here, right? So what I could do, I could have two diodes. Well, the diodes are really made out of diode-connected transistors, so let's show them as that. So these are diode-connected transistors, and if you want to match these well, you probably want to take an NPN in diode-connected like that, and take a PMT in diode-connected like that. Now, the thing is that if you do this, you have a VBE to match this VBE and a VBE to match this VBE. So in that case, if you want to maintain the same VBE across the same, both of them, you have to maintain the same current level as the output, right? Which is too high, because this is the output driver. You don't want to throw half of that current just burning inside a branch. So what would you do to maintain the same voltage level while driving a much lower current into this branch than that branch? Make them smaller, right? The VBEs will remain the same if the currents are a ratio of the saturation currents, the ISs, right? Think about it. If I put two transistors in parallel, that's what we did in mirror, right? If I have a situation like that, VBE1 is equal to VBE2, which means that VT natural log of IC1 over IS1 is equal to VT natural log of IC2 over IS2, which means that IC1 over IC2 is IS1 over IS2. So I can ratio these transistors. So this one has to be much smaller than that. So if this is IS, this is an NIS. And this is IS, whatever, prime. It's NIS prime. And that allows me to have a current that's n times smaller on this side. Now, the way I want to connect this actually to here, right? This one this isn't supposed to be connected there. Now, if I connect that there, the good thing is that that can provide the current, the bias current from that side. But I have to maintain it somehow through here. So I need to point to my bleeding current. Right? That's called bleeding current. So there's a little bit of current flowing there to keep this on. Okay, now, if you look at this stage, let me ask you this question. What is the highest voltage that you can have? Still the same, right? It's a VCC minus VCSAT minus 2 VBEs. VBE from here to there and from the VBE. Now, how about the lowest voltage? What's the minimum voltage? Right, this guy's a transistor, right? This is the collector, so it's like this. The minimum this voltage can be is VCSAT, right? 0.2 volts. And there's another 0.7. So this will be a VCSAT plus a DBE above minus VCC. But at least I have somewhat it's not exactly symmetrical, but I have a much better situation in terms of being able to go negative and positive. Okay? So, now how about the gain? Well, the gain is pretty much the same. Now this time I have to worry about something else, which I will calculate it for you, and in this case, if I properly design it, it should be a major problem. Now, what is the impedance looking into here? Well, that impedance is the parallel combination of impedance looking into here and the impedance looking down. Right? What is the impedance looking into here? It's still the same, right? When the stage has a positive supply, when the output is positive, this guy is on, this guy is off. So I still, for positive values, this is going to be what? This is going to be RL times beta of the NPN, so that's going to be 5 kiloohms. Well, it's going to be actually 7.5 kiloohms, right? Because of the RM of this guy. But I don't know what the current is, so it's a current-dependent value. But the minimum it can have is 5 kiloohms. So 1 milliamp is 7.5. The minimum is 5 kiloohms. So I know it is greater than 5 kiloohms. Right? When the supply is positive. Now, how about this branch? What do I see there? When it's positive, and when I'm driving positive from output voltages. right? So Rm plus Rm, so 2 Rms, right? What is the impedance you see looking down here? Well, this part is infinity, or very large, because it's off. What is this? If it's made out of the transistor, it's Ro. So it's kind of quite a large impedance. So I don't need to worry about that too much. It's the Ro kind of thing. It depends on the current levels, of course, the Ro. So let's say if this were run at 1 milliamp, this would be about 100 kilo ohms. So it's 100 kilo ohms plus 25 plus 25, so it's 1.05 kilo ohms. So then, I'm sorry, sorry, 100.05 kilo ohms. So it's practically the output resistance of this guy, right? Because it's 25 over 25 over 100 kilo ohms. So it's 100 kilo ohms. So this is 100 kilo ohms. This is more than 5 kilo ohms. So practically this is 5 kilo ohms. It's still fair to say this is greater than 5 kilo ohms. And if that's greater than 5 kilo ohms, it's going to be greater than 750. Oh no, I'm sorry. Now it's going to be greater than 500 kilo ohms, which is still okay because then these guys are okay. How about negative swing? When alpha voltage goes negative when I'm in this region of operation. In that case, this guy is off, right? So what is the impedance in that case? It's virtually different. Okay, so in that case, what is the impedance in that case? Well, this guy's off, so it doesn't exist. So what I see looking into here, what do I see? What is the impedance? Well, it is R pi plus this guy times beta. But since I don't know what R pi is because the current levels change, I want to see what the minimum value of this current, this impedance is. The minimum value is when R pi is 0. It will never be 0, but let's say even if the current is very large, it's not going to be lower than beta times RL. But it's beta P this time, right? So that would be what? That would be 2.5 kilo, right? Because it's 50 times 50 ohms, that would be 2.5 kilo ohms. So it's greater than 2.5 kilo ohms, that impedance. Now, what is the impedance looking into here? Because this one was infinite. Now, so this one becomes infinity. This one becomes what? Well, second. Is it 1 over GM? This whole branch is 1 over GM? This is 1 over GM. In series with 1 over GM. In series with this parallel combination where we saw this was about 100 kilo ohms, so I don't need to worry about that. So it's 2.5 kilo ohms plus 250 ohms. Or 2 RMs. So practically it's basically 2.5 kilo ohms. Still. Right? So it's the same impedance, but these guys are much lower impedance than this. So looking into here, practically I see something that's greater than 2.5 kilo ohms. And then looking into here, in that case, I see something like 250 kilo ohms, which is still okay. So I'm dealing with 50 and 100 and 250 kilo ohms. Okay? So this is a semi-okay op-amp. I mean, you can get away with this. Now, we are not done yet. This is not an op-amp yet, because I have the blocks that I haven't really shown how to make, and I haven't shown the biasing circuit. So let's do that quickly now. Well, I know this is going to be a transistor, right? So this is going to be a transistor. So I'm going to just try to turn all of that into actual devices. And this needs to be a transistor. This is a current source, right? So these could be all biased to the same branch, right? But they have to have different values of ISs. They have to be different sizes so to adjust to generate the right current level. Now, what else do I have? I have also a current source up here that I need to fix. I need to take care of. And I have a current source here, which I can, again, use the same branch for biasing, and another one here. So use all of these guys. And now, I want to bias this in such a way that I get my gain properties, for instance, don't change too much, right? So I need a constant GM core. Let's say I want to bias it with a p-tat. So I want to keep my GM constant, which means that I have to make a current source that's proportional to the temperature. So I know how to make that core, right? So let me just erase this stuff. So I need to make a p-tat core, but basically I need to make a VT, K over Q core. I know how to make that, right? So I need a VBE. Well, I can make that up here. And I need to basically create a situation where I subtract 2 VBEs. And to do that, I can do something like this. So if I make this IS n times larger, NIS, this is IS, and then I need one of those floating mirrors. I can make it out of bipolars. Something like that. And then I need the mirror side of it. If you're familiar with this, that's why I'm doing it quickly, right? So that gives me a VT current, reference current. Then I can use that to bias this, and then of course that has to be ratioed with respect to these guys. That PNP, this guy, has to be ratioed with respect to that to get the right value of the current. And then I need to make it also, I need to make another branch for referencing these guys. So I can make another TMT branch through here. So I can copy it one more time, drive it into an NPN that's diode connected, and connect it here. And then since this is driving a whole lot of current sources, I know that I need probably a lot of base current, so I can use that trick. I can put another transistor here, 2 VCC, so this is plus VCC. It's not there. Right? That would be a current source, and this is connected here, that's connected here, and I don't think I have anything other than transistors. Well, I have a resistor here, but I can't have resistors. So this is my entire output. So let's see how many transistors I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I have 27 transistors in this op-amp. But you should be able to tell what each one of them does, basically. What we built it up from grounds up, right? And there are other things we can do to this, actually, and there are some modifications that we'll talk about after we take a quick break. And you can actually make it a lot better than that. So we'll talk about that, and we'll talk about some real op-amps. So let's take a quick break. But well, before we take a break, are there any questions? Yes.
So does the input resistance of the output stage, it being different for the different modes of operation, does that affect the gain by a
Yes,
lot?
your gain becomes both the operation point dependent, right? But your gain is almost always operation point dependent. Even if you look at a common emitter, it's GM RL, but GM depends on the current.